picture, we'll use a circuit diagram. So if I have a battery here, that puts out a voltage, and that is the sort of push power that's going to push electrons. And let's say we have a piece of copper here, and we connect it up to the battery there. The positive side of the battery will push electrons through the copper. Okay, and we can put an ammeter in there which measures the current, and we know the voltage across here. And then we can put another battery in here, so we can double this voltage, and if we do that, we'll find that the current running through the copper is now double what it was before. So we've discovered a simple little law that if we have a piece of copper, we put a voltage across it, a current will run through the copper, and the bigger the voltage, the bigger the current, and the ratio of those two is the resistance.
So George, here at Lancaster, you specialise in experiments at very low temperatures. So how does that affect circuits?
Okay, let's we'll divide this into two pieces. Let's say we have an old-fashioned cathode ray tube like we used to have in televisions years ago. So there's a piece of vacuum here, and if I have an electrode here which has negative charges on it, an electrode here which has positive charges on it, if I have some electrons in here, they are repelled by this negative charge, they are attracted by the positive charge here, and they will simply accelerate from one end of this vacuum to the other. And we could put a phosphor on here, and they would hit the phosphor and light up, and that's essentially the basic idea of a cathode ray tube. But these aren't flowing with a uniform velocity, they're accelerating in an electric field. Now, if instead of having a vacuum, we have a piece of metal, we can have the same idea. With a battery, we can make this end of the metal negative, this end of the metal positive. And what we're going to do is follow what an electron will do as it moves through. Now, if we just, with our vacuum here, if we plot the velocity against the time, as we put an electron in here, it feels this force and it just gradually accelerates. So the velocity goes up uniformly with time. So it accelerates and it continues to accelerate as long as we have the field on. Now, in a metal, the electron here will start to accelerate towards the positive charge at this end. So here's the velocity, here's the time. It will start up here. But the metal is not very pure, say, so we have an impurity. So this electron hits the impurity and it stops dead, and then we'll start off, it will bounce off in some other random direction. And the easiest way of saying, okay, on average it stops dead. So at that point, this velocity goes back to zero, and then the electron has to be accelerated up again until it hits another impurity. So it will go up again like that, then it hits another impurity, stops dead, and it moves through the metal in a series of these little jerky jumps. But if I just average that, this gives me an average constant velocity which the electron is following as it goes through the copper. Okay?
Okay, so what happens with something like tungsten, which is the material that electric light bulb is made from?
Okay, that's a good question. If we have a very nice material, like very, very pure copper, which is what we use for the conductors in electric circuits, we choose that because it has a very low resistance, so it's relatively pure, so it doesn't have many of these impurities, so the electron gets to a much higher velocity before it hits something and has to start all over again. If we want to make an element in a heater, for example, or in a light bulb, we want to make the resistance as high as possible, so we have to have as many of these horrible impurities as we possibly can. So we make it of horrible, nasty alloys, and if we run current through it, it would get hot. So we have to use metals which have high melting points, for example, tungsten, but we need to use nasty alloys which have all sorts of impurities and dislocations and mess. So our poor little electron is doing, never gets up to any velocity, but it's generating a lot of energy, which is what we need.
And that energy comes from?
It comes from the battery. We've had to do work to push these electrons through the system, and the more resistance there is, the more work we have to do. So we're taking the energy out of the battery and converting it into heat.